This is Stylianos. I'm a physics teacher with ATS in Align, and in this video we'll try to solve question 3 from the 2023 AP exam in mechanics. This is the exam page, and as we scroll we will see the basic constants and list of formula that we need for the exam. If necessary, we'll come back to review them, and some tips for geometry and calculus. We solved question 1, which, if I remember correctly, was about simple harmonic oscillations. And we also solved question 2, which was about rotational motion in the previous videos. And we go to question 3, and let's see what it is. All right, what we see on the diagram is a rod that it is about to start rotating down, and as it is about to rotate down, probably will collide with the ball, and later the ball most likely will start moving to the left. So we're talking about rotational motion and collision. And we see the details of the question where we have a rod with mass 2m and L. Also the sphere that has mass m and radius r. We are given the rotational inertia through the pivot, so we do not need to apply the parallel axis theorem. This is the rotational inertia that we can use. And for the ball, also the rotational inertia is given. After the rod is released, the rod swings down and strikes the sphere, as we expected. As a result of the collision, the rod is stopped. This is a little bit important for when we apply the law of conservation of momentum. And the ball slides without rotating. Also, this is important. At the beginning, the ball just moves to the left. It doesn't rotate. And we need to find an expression for the angular speed of the rod just before it strikes the sphere. Well, one way to solve this question for the angular speed, basically, let's try to understand what we need to do. We are given a ball, so we are given a rod that initially is at rest, and it will start rotating until it reaches this position where it will stop after colliding with the ball. So there is a position 1 and there is a position 2, and one way to find the velocity, the angular velocity, just before the collision is to apply the law of conservation of mechanical energy. We can say that we need to make sure that there are no frictional forces. Yes, the pivot has negligible friction, so we can apply the law of conservation of mechanical energy at position 1 and mechanical energy at position 2, they will be equal. So kinetic energy at 1 plus gravitational potential energy at 1 is equal kinetic energy plus gravitational potential energy at 2. And we know for a fact that at position 1 the rod was at rest, so the kinetic energy at 1 was 0. There is no other energy that it is 0. A little bit careful now, because from my experience sometimes students are confused and they say, okay, on the ground the height is 0, at position 2 the rod is in this position the rod touches the ground, so they tend to say that the gravitational potential energy 2 is equal to 0, which is wrong, because the height at position 2 is not 0. The height is related to the height of the center of mass, and the center of mass at position 1 is at a distance equal to the length of the rod, and the center of mass at position 2 is at a distance equal to half of the length of the rod. So the gravitational potential energy 2 is not 0. So we get mass of the rod multiplied by g by the height in position 1, which is the length of the rod, is equal to kinetic energy is 1 over 2. It is rotational kinetic energy, so 1 over 2 I omega squared, and the omega is what we need to find, plus the gravitational potential energy at 2, which is mg height, and the height is half of the length of the rod, so L over 2. Now we can bring this term to the left, so mgl minus mgl over 2 it is mgl over 2 equals to 1 over 2. The moment of inertia is 1 over 3 ml squared multiplied by omega squared. And some things are cancelled out, so 1L and 1L, mass and mass, over 2 and over 2. What remains is G is equal L over 3 omega squared, and our final answer for part A will be 3G over L equals omega squared. This means that the omega will be root 3G over L. So nothing too difficult for part A. We just need to be a little bit careful with the height. Again, from my experience, some students, because they are on a hurry, they say that at the second position the height is 0. No, we are considering the height of the center of mass since we have an extended object. We can move on to part B, where now we need to derive an expression for the linear speed VO of the sphere immediately after the collision. So, right before the collision, we have the rod that has an angular velocity omega O, and we found it that it is root G over 3L, if I'm not mistaken. Actually, no, 3G over L. And the ball that was at rest. And after the collision, the rod stops, so the omega final is 0, and this causes basically all the angular momentum is transferred to the ball, which will move with the speed VO, and this is what we need to find. Now, since we have a collision, we're going to use the law of conservation of momentum, but because the rod was rotating, we will say that the angular momentum before the collision is equal to the angular momentum after the collision. So we're using the law of conservation of angular momentum. The angular momentum is I times omega, so I of the rod multiplied by the omega of the rod. Before the collision, the ball was not moving, so there is no angular momentum. And after the collision, the only thing that it is moving is the ball. But the ball is not rotating, so the angular momentum is the angular momentum for a moving object, for an object that performs translational motion, so it is mvr. So mvr. Now, a little bit careful, I stopped for a minute because I was thinking that this r is capital R, but I was about to be wrong. The r is the distance from the fixed point, from where we measure, from where the rotation happens. So this r is the distance between the ball and the fixed point, and in reality it is the length of the stick. So we can proceed with the I, which is 1 over 3 ml squared multiplied by omega, which was root 3g over L, equals to mvr, and the r is equal to L. The L and 1L can become cancelled. Also, the mass of the rod is 2m, 2 small m, so 1 over 3 multiplied by 2m, 1m and 1m also cancels. And what remains is that the V is equal 2 over 3 L root of 3g L. We can express it in a slightly better way. We can bring the L inside the root, so it will cancel out, and we can also bring the 3 inside the root, so some part of it will be cancelled out. So we have 2 root 3g L squared divided by 3 squared times L. So 2 root, the 3 and the square cancels out, the square and the L cancels out, so g L over 3. This is good enough, but also if we want, we can bring the 2 inside the root, so 2 inside the root, it will become 2 to the power of 2, so 4, so the V is equal root of 4GL over 3, which again is the final answer, and we call this VO. So again, we have a collision. We need to apply the law of conservation of momentum, and in this case, the law of conservation of angular momentum. And we have to be a little bit careful that this r is the distance from the fixed point, which is equal to the length of the rod. Then it is given that, okay, the ball will start sliding, but then it will reach a region with friction. Okay, so we need to go back to the original diagram. This ball at the beginning, it starts moving to the left, sliding without rotating. So either you have a ball or you have a box, it's the same thing. However, when it is reaching region A, there is friction, so now there will be a difference. So the friction acts to the opposite direction of the motion. This friction will cause two things. First, it will cause the ball to slow down, but second, it will cause the ball to rotate. Since there is friction, it will start rotating. So the first thing is we need to do is to represent all the forces. So there is force of gravity or weight, normal force, and the force of friction. Force of friction on the ball. And we need to find later the velocity as a function of time. We said that the velocity will be slowing down, so we need to produce an equation for the velocity and an equation for the angular velocity. Now, again, a little bit careful, when it is mentioned derive, it doesn't necessarily mean take a function and derive it or find a derivative. It means produce an expression for the velocity. Now, we cannot really do this directly. We need to find an expression for the acceleration first, and in order to find the expression for the acceleration, we're going to use Newton's laws. So, F net is equal to ma. I believe that this will be for the linear velocity, and Newton's second law for the angular part of the motion. So, torque net is equal I times A angular. Now, the only force that remains after the normal force and the weight are cancelled out is the force of kinetic friction, and this will be equal to mass times A. The kinetic friction is mu times normal, so mu times mg is equal m times A, so the acceleration is equal mu times g. And since the mu is a constant and the g is a constant, we can apply the law for motion with constant acceleration. So V equals V initial plus AT. The V initial, we have found it. It is 4 root of 4g L over 3. However, since we need to answer in terms of VO and the given constants, I'm just going to write VO. We have already expressed this. One more thing, we said that the ball will slide down, the ball will slow down, so the acceleration should be negative, and one more reason why the acceleration should be negative is because the friction is to the opposite direction of the motion. So either I'm going to express this with a negative on the value of the acceleration or with a negative on the formula. So minus the A, which is mu times g, multiplied by the t, and this is the function for the acceleration. This is the function for the velocity as a function of time. And we need to do the same thing for the angular velocity. So the torque net is friction times the distance from the point of rotation, which is the center of the ball right now, is equal I think that the I was 2 over 5 mr squared multiplied by angular acceleration. The friction was mu times normal, so mu times mg times r is equal to 2 over 5 mr squared angular acceleration. Mass and r uncancelled out, and what remains is that the angular acceleration is 5 mu g over 2r. And now that we have the angular acceleration, and yes, this is also constant, so we can say that the angular velocity is initial angular velocity plus angular acceleration times t. The initial angular velocity was 0, the object was not rotating, so the omega as a function of time is just 5 mu g over 2r multiplied by t, and again this should be our final answer. And we can move on to part E, where we need to find an expression for the time it takes in order for the object to move from point A to point B. Alright, now probably we're going to use one of the two equations that we have produced, but I believe that we need a clue for the distance between A and B. Now we need to figure out if there is a clue given here, which I don't really see. However, there is there is another clue. I'm sorry for that. We don't have a clue about the distance between A and B, but it is mentioned that at point B, the ball begins to roll without sliding. All that time from A to B, the ball was rolling, but at the same time, a part of the ball was sliding. So at point B, we have rolling without sliding. This means that at point B, we can use V is equal omega times R. So we'll take the expression for the omega, we'll take the expression for the V, and we'll say V is equal omega times R. The V is VO minus mu GT is equal omega, so 5 mu G over 2R T multiplied by R. And we'll try to solve this for T. So first thing we need to do is bring this to the other side. So VO is equal 5 mu G R 2R T plus mu GT. A few things are cancelled out, the R and the R. So we have 5 over 2 mu G plus mu G, it will be 7 over 2. So VO is equal 7 over 2 mu times G times T. And from this we bring that the time is equal to VO over 7 mu G. And this should be our final answer for part E1. And again, we need to produce an expression for the linear velocity of the ball when it reaches point B. So again, we'll take this time and bring it to the formula for the velocity. So we had that the velocity was VO minus mu GT, but we have already found the time in the previous part. So 2 VO over 7 mu G. Mu G and mu G is cancelled, so the VO is VO, the V is VO minus 2 over 7 VO. The VO is a common factor, and from this we bring VO minus 2 over 7, it will be 5 over 7 VO, and this is our final answer. And hopefully there will be no more part, and indeed we stop the exam. Now, this was the part 3. It was a little bit long, but all things, quality takes time. All useful things take a little bit long. So I hope you enjoyed this video. Feel free to comment for any part that might not make sense, or if you have any suggestions. I'm waiting for your comments. I hope that you have a fruitful study for the AP exam for all your subjects, and the most important and fun of all, which is physics. Thank you for watching, and have a good day.